Yeah. And here. You press. I go down and get. Yeah.
I will remind everybody that the LTCC cell phone policy is still in play, that you are only allowed to use your phones as a calculator. You may not be using them to text and or be on the internet. Same thing is true, by the way, for your computers. If you are on a computer and using it to access anything other than materials directly related to this class, you're in violation of electronics policy. So make sure that you are working on the materials at hand. As much as we would love this to be a college class, we are not legit a college class. So make sure that you are focused on what you need to be focused on. I know, I love you guys.
In general,
yeah.
Learning outcomes improve the less technology you have around you, which I struggle with because I like technology and I rely on you to have your calculators and be able to do things like use Wolfram Alpha. However, the more you can minimize your distractions, the better you'll learn.
Unfortunately, that is true.
It was always more of a Kesha, we are who we are fan over Lady Gaga.
She's one of those like, I guess,
Sorry. I was gonna get a framed picture of this title.
Oh, wait, could you install names for cheerleading?
But no, there's extra ones for you.
Yeah, but she not said here.
That's gotta be, because you how many grams? One. Okay. What? On what?
I gave you a head start. So start anytime we get a stoichiometry problem. Balance. Find out how many moles you're starting with.
And now I'm back and headed to the view.
But keep going. I'm gonna catch back up.
Yelling at.
I guess he whinies really, really well.
Okay, technology. Bro, shut up. Now, don't you do yourself. My mother's insurance bill is out. Because it. $24. We have to see in your listening. Have to do by 2. Right?
What do we get for moles? I can get close, but get something like something really close to 2.5, just under 2.5 here.
For the first one?
For the hydrogen.
Wait, why are we? Never mind.
Zero.
I'm not loving.
All right. We're gonna get something. If I picked my numbers closely, we should get something close to like 1.2 for the carbon monoxide. All right. How can we tell what's going to run out first?
Yeah.
How do we know that? Not real hard. Going on vibes. If we get the hang of doing this, this is a 2-to-1 ratio, right? So we're using up the carbon monoxide twice as fast. If you can double this number in your head and compare it to the number next to it, we can see what's going to run out first. Doubling this is 2.464, so a little bit less than this. So as much as it pains me to admit it, Ava's right. So this is going to run out first, or carbon monoxide is going to run out first. So that allows us to fill in one entire column here, right? Because we know we're running out of that. Which means we know what X is as well. And the nice thing about the one running out that has a coefficient of 1 means that is X is going to be 1.232. Can everybody see how we're just using similar tools the way we did limiting reactant problems before? We're just showing it a little bit differently with the ice table. And you can still do it the old way. The old way still works. In my mind, thinking about it this way helps me when I care about more than one thing at a time, though. So X is 1.232. If we guessed, here's the other thing about limiting reactant. If we guessed wrong, if we said this was going to run out first and we were wrong about it, when we try to fill out, when we solve for X and try to fill out the rest of this, we're going to get a negative number somewhere. You can't have a negative number for your final amount of any of these. So that would be your clue that you did it wrong. That you should go back and pick the other molecule as your limiting reactant. So then what do we get? 2.480 minus 2x gives us 0.016. Nope, not this time. Those of you using calculators, tell me if I did that wrong. And that means we can fill this part in too, right? As soon as we know X, we can fill in everything. Did I miss something? We looking good? Okay. So final question. We've answered a lot about the reaction already, right? We know what the limiting reactant is. We even know what an excess reactant in our theoretical yield is in terms of moles. The last part here says, what's the final pressure if we have an initial pressure? So we've got something changing, right? Which means we know that volume and temperature are constant, but we don't know what they are. So we can't just use PV equals nRT in this case. What's the other version of the gas laws that we could use that involve things changing?
Fibner.
And it's the other version
Nerve.
of Fibner. So what can we do now that we know that volume and temperature are constant? What happens?
Yes.
If they're constant, they're the same on both sides of the equation, right? They're the same on both sides of the equation. We can just divide both sides by the volume, multiply both sides by the temperature, everything cancels out. So not everything. Volumes and temperatures all cancel out. And we get some new version of the gas laws that'll be more useful in this case. So what can we fill in now?
pressure vessel, pressure one.
Pressure 1.
And both the ends.
We can fill in N1 and N2. We're talking about total moles, right? So we're just going to add up each row. Our N1 is going to be the sum of these. So 3.7712. If I carried my number properly. And then down here we get 1.248. All I did to get these N1 is just adding up the initial column or row. N2, add up the end row. Now we know everything except P2. Plug and chug.
So rinsing out.
1.51 ATM. 3.712 moles. 1.248 moles. Reasonableness check. What should our answer be pretty close to? How'd you get there, BD? Not twice as big. It's about 3 times as big, right? We started with 3.7, which is almost exactly 3 times bigger than what we ended with. So we should end with about 1/3 of the pressure. So final answer is really close to 0.5. Is it 0.50 something?
So.
549 459 499. All right, so for this class, I don't know if we have a take-home final scheduled. When I do take-home finals, those are when I do like problem-solving word problems, stuff that you haven't seen quite as much before. And for this class, it's usually 2 problems. One's going to be a spreadsheet problem where you have to do some calculations, make some plots, and then maybe solve a small out system of equations. And then the other one is going to be some sort of stoichiometry problems. Not something as hard as number 4, but certainly something like this or something like number 2 are fair game. We'll talk more about the rules for that when we get closer to that. But the whole reason we keep doing word problems with stoichiometry is because it's going to come back on the take-home final, right? You had a practice midterm, right? Before the week before that, we'll do the same thing. That's the way I do all my in-class finals. So you'll get a practice test a week ahead of time. That'll be your last homework assignment. Will be do the practice test and turn it in for points. So no surprises, don't even really have to do any critical thinking on the in-class final. There's going to be, I guess I shouldn't say that. There's going to be 1 problem out of 10. Number 10 is always the wild card problem. Make you do a little bit of thinking on your feet. That'll separate the A's from the B's on the test. And then you'll also have, if you're good at critical thinking, but not under time stress, that's what the take-home test is to make up for. So I'm going to make you do a little bit of critical thinking, work in groups, do some problem solving, but you'll have a whole week to do it. And you'll be able to ask me questions, work in groups, things like that. So that's where you're going to see a problem like this might show up again in the future. Not on the in-class final, but it's definitely not something you can just write off because it's coming back.
I think we should just watch Ratatouille.
Just watch Ratatouille.
This
You'd have better Oppenheimer or Interstellar both be better choices. But y'all have seen that already.
You know what Christmas party watch almost.
Oppenheimer, I think needs parental approval, probably. Close to.
Yeah. Us 14.
All right. As long as we're off topic, let's talk about next week. What?
Yes, wait.
What'd you win?
Only us two.
What'd you win?
The critical thinking.
The Critical Thinking Award. All right, then you should do great at the take-home final.
They just didn't know. Yeah.
Who here has seen Interstellar?
I think
People. Maybe that's what we could do next week when I'm not here. Interstellar might be a better choice. I'm not contracted to be here. I'm off. This is finals week for the college. My break, I have to be grading my other classes. All right. Last relevant piece for Interstellar. Interstellar has the single best description of chemistry I've ever heard, or statistical thermodynamics, I should say. It's the way that they describe Murphy's Law. Who remembers the way they phrase Murphy's Law in Interstellar? What's Murphy's Law the way you know it?
Who knows it?
Anything that can go wrong will go wrong. It's better phrased as anything that can happen does happen.
It's giving deep.
And that's exactly how chemistry works. It turns out, this will be relevant. We're going to start talking a little bit about thermodynamics and statistics later on in this lecture, if we get to it today. But basically, turns out all chemical reactions can happen at least a little bit. Sometimes they just happen so slowly that if they started at the beginning of the universe, they still wouldn't have a measurable amount of product formed yet. But technically, they do happen. Everything happens. It's all just about how often and how quickly it happens. And I really enjoy Interstellar for that one line, if nothing else. It's a really good physics astronomy movie. They did all the science right up until the part where he falls. Never mind, I can't say anything because half of you haven't seen it yet.
Yeah. It's a good movie.
It's a very good movie. That's something we'll consider for next week. All right. What am I doing next? Let's talk about. We could watch Good Eats with Dalton Brown, maybe. So many objects. You could learn what gluten actually is.
Stomach bar.
All right, new material. This is the second to last topic in this class. So we're going to talk about intermolecular forces and phase change today, and I think I'll probably be here one day next week. So we'll talk about intermolecular forces and phase change, and then when we get back from break in January, we're going to talk about radioactivity, and we're going to talk about nuclear reactions, and we'll get to use the most famous physics equation in the world. Bingo. Oh, Emiliano got it. E equals MC squared. You'll actually get to use E equals MC squared in January. Turns out it's actually really easy as long as you pay attention to your sig figs.
Nice.
So, but until then, we still have to talk about other phases. We just finished talking about gases. We're going to talk about what causes gases to turn into other phases. So first off, who remembers what those assumptions were that we used in order to use any of the simple gas laws or the ideal gas law? We had to make some assumptions. Anybody remember what they were? What were we assuming the gases did or didn't do? No phase change.
It's not equal to zero.
And really, we're saying no interactions.
This is probably where you want to get your notebooks out.
So first assumption was no interactions between molecules, which the extension of that, the conclusion of that is no phase change. And what was the other one? Gases have the gas molecules have volume of 0. So one more note about the final. Star this. This is the third time I've put this on the board. There, I'm going to put this on the in-class final. This is one of the questions. I might ask you what that means. I might ask you to interpret it a little bit, but one of the questions on the in-class final will be, what are the assumptions in the ideal gas law? Hold your horses. So if we're assuming no interactions between the molecules, that means there's some time when this is not a good assumption. If this is an assumption we have to make, if it's not just true, that means it's gas molecules have interactions between them. If gas molecules run into each other, they will interact in some way. Those interactions are what we're going to talk about next. All right, so what holds the molecules together are called intramolecular. Intra means within. Inter means between or across. So intramolecular forces are the bonds we've already talked about. Ionic bonds, covalent bonds, things that hold the molecules together. Intermolecular forces are not quite as strong, but they're still an attractive force. All right, and so we want to be able to look at a molecule or a system and have some idea of what those intermolecular forces are so that we can do things like predict what has a higher boiling point. What substance, what substance is going to go through a specific phase change at different temperatures? Which one's going to have, what's another, oh, we'll get to those in a second. We got to define some other terms. All right, so what causes an ionic bond? What is an ionic bond? What's an ionic compound look like? More specifically. Okay. Instead of what holds it together, what is an ionic compound? Versus a covalent compound.
Cation versus anion.
Cation versus anion. Good. What does that mean? What is a cation? Positive charge. So ionic compounds form ionic bonds just because you have positive charges and negative charges. Opposite charges stick together. That's going to be the basis for all of our intermolecular forces, is positive charges and negative charges stick together. These, they're not always as strong as a full +1 and a full -1. You talk about polarity when you talked about your Lewis dot structures. We talked a little bit about that, right? I think that's right about where I took over. We talked about how to determine if a compound is polar. What did polar mean? If I looked at the Lewis dot structure for water, is that a polar molecule? Who remembers what the criteria were for finding whether or not a molecule was polar? Okay, So polar molecules, polar by definition just means that part of the molecule has a partial charge. It's got like a little bit of a charge. It's not a full-on ion. But if you have one part of the molecule that's better at pulling the electrons towards itself, even though the entire molecule might be neutral because of the number of protons and electrons, oxygen is more electronegative than hydrogen, right? Where was the most electronegative elements found?
Over yonder.
Over yonder, top right, excluding the noble gases because they're boring. So nitrogen, oxygen, fluorine, and chlorine. Basically anything that was in a covalent bond with nitrogen, oxygen, fluorine, or chlorine was going to have a polar bond. And a polar bond just means that, okay, these electrons right here, they're being shared between a hydrogen and an oxygen. They're in both valences at the same time. But they're not being shared evenly. And what is our definition of electronegativity? What does electronegativity mean? It just means that they're good at pulling electrons towards themselves. So all the nuclei on the periodic table, they all have a nucleus with protons and neutrons, and they're surrounded by electrons, right? You can think of the electrons as being like covers on a bed, the blankets on a bed. Anytime that you have a covalent bond, it's like blanket is being shared between two people. But if it's not being shared evenly, they don't both have the same access to the blanket. Anybody ever had to on a family vacation share a bed with a sibling that was a blanket hog? Right? That's a polar bond. Polar bond, the more electronegative elements are the bullies, they're the blanket hogs. And if you force something that's less electronegative to share a blanket with something that's more electronegative, all the blankets, all the electrons wind up on the more electronegative element. So even though this entire molecule has a charge of 0, within this bond, you're going to have a little bit of a positive charge and a little bit of a negative charge. Right? And the way we differentiate, so we're not saying the same thing as an actual ion. In chemistry, we use this lowercase delta. That just means it's a partial charge. It's not a complete +1 or a complete -1. It basically means they're sharing the blanket, but they're not sharing it evenly. So if that's the case, this entire molecule is going to have a partial charge on one side of it versus the other, right? Because we have this oxygen that's more electronegative than both of the hydrogens, so it's pulling all the electrons towards itself. This whole side of the molecule is a partial negative. And this whole side of the molecule is a partial positive. Now, what was it that held our ionic compounds together? Positives and negatives attract, right? So what would happen if a water molecule bumped into another water molecule?
Join together.
They have a tendency to stick together. Because if this water molecule gets bumped into by another water molecule, the partial negative on this water molecule is going to be attracted to the partial positive on the other water molecule. So this is your first example of what an intermolecular force is. The intramolecular force is the covalent bonds that are holding this whole water molecule together. The intermolecular force is, okay, well, even though this is its own molecule, it still has these partial positives and partial negatives, which means when they bump into each other, they're going to stick together. Right, so is it a good assumption for water that the molecules don't have intermolecular forces? Is the ideal gas law work very well for water? No, because water does have strong forces kind of holding the individual molecules together. If we took a bunch of water molecules and forced them into a small area and then dropped the temperature so they all slowed down, what happens? What happens if you take water molecules that are a gas and you cool them down and you force them into a smaller area? Phase change. You get a liquid, and then beyond that, you're going to get a solid. Right, so these intermolecular forces have macroscopic consequences that we can see. Things that have stronger intermolecular forces it's going to be easier to put them into a liquid in a solid state. Not everything does that. And what is a molecule that has a really low boiling point? Like what gets used in Hollywood movies for like, oh, something's really, really cold. Salt. Not what I was looking for.
Here, wait, let me.
I think they used it in Terminator 2. Who's seen Terminator 2?
Baby powder.
Not sure where you're going. Liquid nitrogen.
Yeah.
In liquid nitrogen, in Terminator 2, the T-1000, they freeze him in liquid nitrogen and then he shatters into 1,000 pieces, right? Again, if you haven't seen that movie, you should go watch that movie. It's classic. Don't bother with Terminator 1. It's not that good. They use it. It was good at the time. I'll give you that. Yes, if you go to the doctor and have a wart, they'll use liquid nitrogen to freeze off your wart. They won't give you that at home.
Okay, so where are they still here?
Talk to your doctor. I'm not a dermatologist.
I'll do it for you.
All right.
Future.
Is not liquid nitrogen going to have the same level of intermolecular forces? What is liquid nitrogen's, or not liquid nitrogen, was nitrogen's Lewis dot structure going to look like? Let's review how to do Lewis dot structures. That's part of this part of the class. What's our first step for doing Lewis dot structure? The middle one. What if we don't have a middle one? We know that there's going to be two nitrogens and that they're attached to each other. And then other than that, we total up our total valence electrons and see how we have to arrange things so that everything has a full valence. That's our end goal, right? Our primary goal with the Lewis dot structure. So nitrogens each come with 5 valence electrons. So we have 10 electrons total. How many electrons did we use to bind these together? 2. So 8 electrons left. How many we'll start with the left-hand nitrogen. How many does this nitrogen still need?
6.
Needs another 6 to get, because we want to fill the valences, right? We're not just trying to get back to where it was on the periodic table. We want a full valence shell.
Where's this going? You explain
Can I explain what?
the
Number of valence electrons we have to work with. We only have a total of 10 valence electrons to work with, but we need to fill the valence shell for both nitrogens. We just used another 6. So how many do we have left? 2 electrons left. Where should we put them? Can we put them on this nitrogen? It's already got a full valence, right? So we only have one other option. Is that a good Lewis dot structure? Why not? It's got 4 valence electrons, but it still needs 8, right? Well, can I just do this? Why not? We don't have those electrons. We only had 10 to work with. So we have to make this nitrogen share more. Take a pair of electrons, erase it, and turn it into another bond. Are we good now?
No.
We're closer.
Triple bond.
You got to do it again. Now we're good, right? Our criteria for a good Lewis dot structure are, let's see if I got my grammar right. The criteria are use the right number of electrons is the number one priority. We can't use electrons we don't have. What's the second priority? Don't have to necessarily be shared equally, but we do need to fill the valence shell. They are going to be shared. We know that they're bonded at least one, but they might not be shared evenly necessarily.
No.
So full valences. Did we talk about formal charge? Okay. Then we'll leave that one alone for now. We could say yes if we use the right number of electrons and everything has a full valence. Therefore, it's a good Lewis dot structure. Is it a polar molecule? Nitrogen's really electronegative, right? It's in that top corner. Is this going to have a polar bond?
Yes.
Let's go back to our blanket hog analogy. Two people have to share a bed that are both blanket hogs. Does the blanket have any net motion one way or the other? No, they're fighting over it all. It might not be a good night's sleep either way, but at the very least, it's going to be evenly shared, right? So even though nitrogen is really electronegative, nitrogen is fighting with another electronegative element or fighting with another nitrogen. The other analogy you could use, tug of war, works as a pretty good analogy. Those big four, nitrogen, oxygen, fluorine, and chlorine, those are like NFL teams playing tug of war. If you have two equally strong NFL teams playing tug of war, what happens to the rope? Stays in the middle. That the Pro Bowl, any NFL fans in here? The Pro Bowl is a relatively new invention. Before the Pro Bowl, what they would do is the two teams that were in the Super Bowl would go to Hawaii the week after the Super Bowl, and they would do a bunch of games against each other. One of which was pick 5 people from each team and do a tug of war. And so it was always the offensive line from both teams playing tug of war against each other. And there's a video of, I don't remember what year it was, but these two teams that played tug of war for over an hour. And neither one of the teams had just lost the Super Bowl the week before. Neither team wanted to give up. And so they played tug of war for an hour and the rope did not move. They called in subs. They had to switch out in the middle. It's because they were getting too tired. That's what nitrogen's doing here. They're really strong, but they're equally matched so that those electrons aren't going anywhere. So nitrogen has very little in the way of intermolecular forces because there is no partial positive and partial negative in a symmetrical molecule like this. And so that's why nitrogen has such a low boiling point. It boils at 70 Kelvin, 77 Kelvin, I think. It's about minus 200 Celsius, so about minus 400 Fahrenheit. Pretty cold. Because of the intermolecular forces, or the lack thereof. All right, so we went a little bit into the review here. Let's define. All right, so here's our criteria for doing a good Lewis dot structure. Right number of electrons, everything has a full valence. We need some criteria to determine whether or not we have a polar molecule, because that's the other piece that goes into this. If we have a polar molecule, Polar molecules, you have to be able to say yes to both of these. You have to have polar bonds. And you have to have asymmetry. So nitrogen's electronegative, but it was a perfectly symmetrical molecule. So it's not a polar molecule. All right, so, and let's define polar bonds. We're just going down a rabbit hole. We just have to keep redefining things, right? So I've used some of these terms, but it might have been a while. And this is right exactly when there was some discontinuity in the class instruction. So what's a polar bond? Polar bond is when you have a blanket hog and something that can't hang on to the blanket, right? A polar bond is an NFL team playing tug of war with a high school football team. No shade to our high school football team here, but even the Raiders, as bad as they are, would absolutely destroy our team when it came to a tug of war contest, right? So we need polar bonds. We need a difference in electronegativity. So, and we have values for electronegativity too. Let me. We'll just use. So on your final, I'm going to give you a periodic table, an abbreviated version that has electronegativity values. There's numbers for electronegativity, named after one of my favorite chemists, Linus Pauling. Linus Pauling is the best chemist of the 20th century, if you ask me. He is one of, other than Marie Curie, he's the only other person ever to win a Nobel Prize in 2 different disciplines. Chemistry, and he won the Nobel Peace Prize because he worked on nuclear disarmament in the 60s. He lived in Big Sur in the 60s when all the folk rock stars were moving to Big Sur from LA. So he got to hang out with Neil Young and the Byrds and things like that. Yes, there's a really good picture. Here's how you knew he was a really big deal. It's Rolling Stone interviewed him. And when Rolling Stone is interviewing a chemist, I mean, that's sort of the definition of a rock star chemist, right? So these are in degrees Pauling, after Linus Pauling. I guess a humble brag about Linus Pauling. I had to teach his great niece. She took chemistry at the community college up here.
So did you figure it out?
Her last name was Pauling. She told me when we covered Linus Pauling, and I kept talking about him like this, like, that's my great uncle. I stayed at his house for Christmas last year, which my jaw dropped at that point. All right, so here's our definition for electronegative bonds. You need a difference in electronegativity greater than 0.4. Difference in electronegativity greater than 0.4, which is sort of an arbitrary number. Basically, they chose 0.4 because one of the most common non-polar bonds that you can have is carbon to hydrogen. And carbon, so basically anything that's a bigger difference in electronegativity than carbon to hydrogen, we call that polar. That's sort of our dividing line. Because carbon to hydrogen is nonpolar. It's not entirely arbitrary, but that's the way that I remember what this cutoff is. It's use carbon and hydrogen as your dividing line. If you have a molecule that's entirely carbons and hydrogens, it won't dissolve in water because water is too polar for it. And so they sort of use carbon and hydrogen as your definition of nonpolar because it won't dissolve in water. And so anytime we're trying to decide if a molecule is a polar molecule, we've got to do a Lewis dot structure. When you do the Lewis dot structure, you'll be able to see what types of bonds you have. So when we looked at water, we had oxygen to hydrogen. So our difference in electronegativity, oxygen's 3.44, hydrogen's 2.20. So our difference in electronegativity, 3.44 minus 2.20. We get 1.24. That's bigger than our threshold, right? So that means we have a polar bond. Do we have asymmetry? That's the other piece of this. Is this an asymmetric molecule?
Just enforce the bonds. Really.
And kind of where they're positioned. Let's talk about asymmetry then. It's one more example with electronegativity before we move on to asymmetry. Is that going to be a polar bond? Do you even need to look at the table? Anything bonded to itself can't be a polar bond, right? Because by definition, nitrogen here and nitrogen there are going to have the same electronegativities. All right, so let's talk about asymmetry, because that's a little bit weird, but there's a really easy way to define it. Because remember, these are not just flat molecules. They exist in 3 dimensions, right? Remember when we talked about Vesper geometries and tetrahedral and trigonal planar and all that? Basically, in order to have asymmetry, you need at least one thing around your central atom has to be different than the others. Because if we had a molecule that looked like this. This is a molecule gets used all the time in chemistry. I think it used to be used in dry cleaning actually as well. They used to call it dry cleaning not because it didn't use any liquids, but because it didn't use any water. So they used a liquid called carbon tetrachloride as a dry cleaning liquid. Does it have polar bonds? Carbon's 2.55, chlorine is 3.16. That's a bigger difference than 0.4, right? So it's got polar bonds, but does it have any asymmetry? Because everything around this carbon is totally symmetrical, you're not going to have any net movement of the electrons. If the chlorines are our NFL teams and carbons are Pee Wee football team, it doesn't really matter because the carbon's stuck in the middle. The Pee Wee football team is hanging on to the middle of a 4-way tug of war. Nothing's moving, but they're going along for the ride. Whatever happens, but nothing's happening because all of these chlorines are exactly opposite of each other in opposite directions. So they cancel each other out. As soon as we do that, it's asymmetric. Right? Because now we have 3 chlorines kind of canceling each other out, but not exactly canceling each other out. And then we have this hydrogen that's not canceling anything out. Right? So when we say asymmetry, it just means that one of the groups around the central atom is not the same as the others. Why would you say that? They're the same. There's things that are different around that central atom. But remember, this isn't actually existing in this flat state. Really it's tetrahedral, right? Which means if we actually drew this in a tetrahedral shape, we'd have oxygen here, lone pair about 109 degrees apart, a hydrogen going into the board and a hydrogen coming out of the board. So yeah, it kind of looks symmetrical when we draw it like this. Like, how do we figure out if there's a mismatch? But when we draw it like this, we can see, okay, well, this hydrogen and this hydrogen are symmetrical, so they might kind of cancel each other out, but they're both kind of vaguely pointed down and to the left, right? Which means the oxygen is still pulling opposite of those. Even if they partially cancel each other out, this whole side of the molecule doesn't have those hydrogens canceling anything out. So as soon as you have one or more things that are not the same, you've got asymmetry. There are a couple fringe cases where you could have things that have where you have other symmetry and they will still wind up canceling each other out, but not till you get to 5 electron groups or more. For anything tetrahedral and down, in terms of these geometries, one thing or two things that are different means that you have asymmetry. And as soon as you have asymmetry and you have polar bonds, you get a polar molecule. All right, let's do another example. Hey, I'm trying to come up with a good one that's not going to be a trick question anywhere. How about ammonia, NH3? Is it a polar molecule? How do we figure it out? Well, if it's a polar molecule, we need to figure out the Lewis dot structure in order to figure out if we have polar bonds and asymmetry. So what is the Lewis dot structure going to look like? How many electrons do we have to work with? So we get 5 valence electrons from the nitrogen plus 1 from each hydrogen. So 5 electrons plus 3 hydrogens, each of which brings 1 electron to the table. So what's going to go in the middle? Nitrogen or a hydrogen? Why? Can hydrogen ever go in the middle? Why not? Because it can only have 2 electrons. Look where it is on the periodic table. It's in that first row, which means you can never have a hydrogen with more than 2 electrons. Which means hydrogen can never make more than 1 bond. Which, if you think about the logic of that, means hydrogen can never go in the middle. Because in order to go in the middle, you have to be able to form at least 2 bonds, right? So hydrogen will never be in the middle, which means in this case, it's got to be nitrogen. And do we have to worry about something like that happening? No, for the same reason, right? How many electrons have we used by drawing that? 6 electrons. So 2 electrons left. Where are they going to go? Lone pair on the nitrogen. Good. They can't go on the hydrogen because the hydrogen will never go above how many? 2. 2 electrons, 1 bond. Did we use the right number of electrons? Did we have, everything has a full valence? We're good. Now we can think about, is it polar? Why? Does it have polar bonds? Is nitrogen to hydrogen polar?
Yes.
Yeah. Nitrogen's one of our, even if you, without even looking at our values here, as soon as you see something, one of those big four bonded to pretty much anything else, that's a polar bond. Right? You can split hairs a little bit. Like you could have nitrogen bonded to krypton, it turns out. And that's not a polar bond by these values. That's like a really rare fringe case. For the most part, in the real world, if you've got anything from on Mount Rushmore here, bonded to anything else, Mount Rushmore, nitrogen, oxygen, fluorine, chlorine. It's the only way you use that phrase, isn't it? So we have polar bonds and we have asymmetry because we have hydrogens and one thing that's not the same as the others. Okay. How do we feel about that?
Fantastic.
Good, because this is going to be 10% of the in-class final. Is going to be, here's two molecules. Draw the Lewis dot structure, tell me the geometry, and is it polar? Right? So this is going to come back again, which is why we're spending the time to review it now. Let me go back to the slides now. Where did I lose it? We'll just do it this way.
So this was the right of your task.
Oh, that is it. There we go. All right.
Whoa, yeah.
All right. So let's take these intermolecular forces and talk about what that does in terms of phases. If there's no intermolecular forces, not in general, if there's no intermolecular forces, your molecules will always be a gas. That's why the ideal gas law works. If you have zero intermolecular forces, then when these things bounce into each other, they just bounce right off. They don't stick together. You will never get it to form a liquid if you don't have intermolecular forces. If you take that liquid and you slow the molecules down enough, then they get locked into a solid. Basically, a solid, if you think about the way we talk about temperature, temperature was just a way to talk about how fast the atoms are moving, right? So when you slow these things down, they have a tendency to stick together. And when we have things where their attractive forces, the intermolecular forces, are stronger than the energy that the atoms themselves have, then they're going to stick together and you're going to see a phase change. Right? The more you slow things down, the more they're going to tend to stick together. Because if you give these atoms enough room and energy, they're not going to stick together. If you give it energy by increasing the temperature, they're just going to fly around forever. Think about it. It's kind of what this picture looks like. If you think about putting a bunch of ping pong balls into a moving box, if you're shaking them at a constant rate, they're never going to settle down into the bottom, right? That's kind of like temperature. How fast you're shaking it is how the overall temperature of the system. What if you replaced What if you took the ping pong balls and you used some, like, I don't know, spray glue or something on them and then put them back in there and shook the box? Are they still going to be flying around randomly? And then it gets a little bit trickier, right? It depends how hard am I shaking the box. If I shake the box just a little bit, where before they might have just been bouncing around randomly, they might tend to stick together and form these globs that are going to be kind of analogous to a liquid. And then if you slow it down enough, the glue on ping pong balls falls apart a little bit when we start talking about crystalline solids. Because crystalline solids is this. This is a crystalline solid. Everything's sort of locked into position. And that tends to happen really, really well with ionic compounds. Because if this was sodium chloride, what do the red and the white represent? Sodium and chloride, opposite charges, right? Are you ever going to see a chloride next to another chloride? No, because opposite charge, or if they're both negatives, they're going to push each other away, right? Water, it turns out, does the same thing. That's why ice has a nice crystalline look to it. It's because water is a polar molecule. When you slow down water molecules enough, they turn into a liquid, but then they'll settle into these stable states that we call a crystalline state. Let's see. So you get something that looks like this. All of these water molecules are all arranged so that the oxygen is pointed towards a hydrogen. Because what's the charge on an oxygen in a water molecule? Partial negative, right? And all of the hydrogens are partial positives. And when you zoom out enough, you can see it winds that repeating pattern. And I'm stressing the GPU out on this thing. That repeating pattern is what makes something crystalline. Let me find the right, there it is. That's all a crystal is when you get this repeating pattern that goes out for a mole at a time. How big is a mole? Not that big? Kind of big. 10 to the 23rd. So for reference, this is a thought experiment that I did with my high school teacher. If you covered the surface of the earth in a mole of ping pong balls, it would be close to a mile deep. The surface of the entire planet would be covered in almost a mile of ping pong balls if you had a mole of ping pong balls. If you had, there's also a good thought experiment. If you had a mole of moles, like a mole, that number of small fuzzy rodents, it would be roughly the size of the moon. So pretty small number. So if you repeat this, but at the same time, you're right, it's not that big of a number in terms of what's a mole of water molecules weigh? Only about 18 grams.
I actually have a mole of water on my desk. Here's a mole of water.
There you go. In that cup is 6 times 10 to the 23rd water molecules. So when you make a water crystal, when you make an ice crystal that has a nice crystalline shape to it, you get this repeating structure that goes off almost infinitely in terms of like rounding. It goes off so far in every direction, we can't even stop it. You can't even fathom it. Random unit facts, since you brought up the word fathom. What is a fathom? Anybody know? It's used in nautical applications for measuring how deep the water is so that your ship didn't run aground during the age of sail. Fathoms about, I think it's 6 feet. Basically what they would do on old sailboats is they would just have a rope with a piece of lead tied to the bottom. They would just drop it down until it hit ground, and they'd use that to measure how deep the water was. And they just had that rope just had a mark every 6 feet.
2 yards.
2 yards. All right. Let's look at, again, I keep walking over there to change my slides. So these intermolecular forces, how do we classify how strong they are? So we already figured out, okay, if we have polar molecules, we have intermolecular forces. But how come ammonia, for instance, doesn't have the same, yes, similar intermolecular forces to water, but it boils at, I want to say like minus 20 Celsius. It boils well below freezing. Boils, mind you, not freezes. It boils at minus 20 Celsius. And water doesn't boil till 100 Celsius. So we need some way of classifying these intermolecular forces. We can kind of see the logic of the stronger the intermolecular force is, the higher the boiling point is going to be. But we still need a way to classify that. All right, so this whole category of when you have partial charges, you get some attractive forces. They're also called van der Waals forces. After the, I think he was Dutch, maybe Belgian, I think Dutch, scientist who first did a lot of the theory here. And the simplest version is what are called dipole-dipole interactions. Dipole is just another way of saying a polar molecule. If you have a polar molecule, it is a dipole. Because you can't have a polar molecule without having a partial positive on one side and a partial negative on the other. And if you have two poles of a magnet, that's the definition of a dipole. Di means two, pole means charge, kind of. There's interesting field of research where they're trying to create a material that is magnetic, that's not a dipole. But to my knowledge, they haven't been successful with that. And they've been working at it for 60, 70, 100 years. So everything that has a charge that is a polar molecule is a dipole. And then there's some specific instances called hydrogen bonds and dispersion forces that are kind of like modifying those dipole-dipole interactions. Hydrogen bonds in particular are a type of dipole-dipole attraction where one of the molecules involved in the polar bonds is a hydrogen. And I think so. This is just a demonstration of figures showing what dipole-dipole attractions are going to look like. If you have a bunch of molecules with a partial negative and a partial positive, they're always going to kind of arrange themselves in that shape, just like that water crystal. In this case, this is the red lines are showing attractive forces, and the blue lines are showing repulsive forces, the forces that are pushing each other apart. And you'll notice that in this somewhat random looking figure, basically you're never going to get these two that close together. In fact, it's missing a blue line there. I didn't make this figure. Apologies. But overall, you're going to wind up with these things where you've got the red lines are closer together than the other. In fact, this molecule right here is not really in a very stable state, right? It probably wants to flip around a little bit because right now you've got a negative charge next to another negative. And you've got a positive kind of close to another positive. If you flipped that around, it might be more stable. And that's kind of what makes something a liquid versus a solid. Is a liquid, the molecules still have enough energy that they can move around and sort of flip back and forth between different states. If you get it cold enough, they're going to settle in and be kind of locked into one configuration. All right, so if you have hydrogen participating in a covalent bond with any of our big four, nitrogen, oxygen, fluorine, chlorine, then you get a special case of dipole-dipole attractions called hydrogen bonds. Because what's unique about hydrogen compared to something else that has a low electronegativity? Where is hydrogen on the periodic table? At the very top, right? It only has valence electrons. It doesn't have any electrons underneath its valence shell. Which means if its valence electrons are in a covalent bond with a polar element, basically it's being pulled entirely away from that nucleus. You basically get the nucleus of the hydrogen atom is almost completely bare. And so you get stronger intermolecular forces when it's hydrogen with one of the big four compared to anything else. So they get their own classification. And that's, I guess that's as we only have 2 minutes left. We can do one more and then we'll review this when I come back. Workday. So finishing your lab tomorrow. Whatever else you still have left to turn in.
Do you need them to run a second trial in the lab? Or do you want them to?
Might as yeah, let's do a second trial. If you haven't done that yet. All right, last concept. The other type of dipole-dipole attraction. I know we're almost done. Hang on 1 second. I just want you to hear this once now, and then I'm going to say it again another time, but I want you to hear it once today. Even in a completely non-polar molecule, there's still some attractive forces. Because if you have a bunch of electrons randomly moving or existing as a probability cloud around the nucleus, there's some probability that, say, for this helium atom, there's a finite chance that you get both electrons on the same side of the atom at the same time. It's not going to be very stable that way because those two electrons are going to push off against each other and try and wind up back on average on opposite sides. But the fact that they can temporarily be on one side of the molecule means you can create a dipole, very, very short-lived dipole. And that means that even completely non-polar molecules have some attractive forces because everything has at least some electrons. And as long as you have some electrons, you can have these, what we call dispersion forces. Even though they're temporary, you can still have something that's completely non-polar, like wax is a good example. Wax is a completely non-polar molecule, but it must have intermolecular forces because what state do you find wax in at room temperature? It's a solid. The only reason is because of these. All right, tomorrow's work day. If you haven't finished the gas loss problems, you can turn them in tomorrow. I'm going to change the due date on Canvas if you haven't finished it yet.
Thank you.
Thank you. Have a good day.